we have this schematic. Switch will be turned in time 0. This will be our capacitor. It's variable. I can change capacitance. 1 nanofarad. So what will be voltage? I think I should call the point flow. Students don't know. Can we say value before 0 time? 0 and after? Capacitor is charged to the full voltage and it discharges through resistor. 1 second. We will get something like this. This is time, up and down. This is 0 and this line of the alpha is 1 decrement constant. Quasics of transit. I will simulate this network, but in a different way. Oh. Yes. I will use generator producing pulses 1 microsecond will be length of pulse and timing let's say something like 1 millisecond. This is grounded and here will be my capacitor. Resistance and this will be output signal. Possible. This will be my resistance box, 100,000 ohms. I hope something
something will work here. 1 second, I'll assemble my network. One second, network will. I need this here. This goes. No green bars, because I got the green bars. And fire from the scope. Fire from the scope. Yes. Yeah. On. Electricity. I forgot to. Okay. I think this one is okay. Ah, this one is good. What a nice sequence. See how it works. On each pulse of the generator, capacitor claims pulse, input of 5 volts. Capacitor charges and then discharges to a resistor. I made a sequence of a periodic signal. Is it periodic? It repeats? Yeah, it repeats with the frequency set by my
this one, with the frequency set of my generator. Okay, 1.5 microseconds. No, one microsecond. Pulse charges capacitor and it is discharged. Nice. We have frequency, we have effective value. Now question. Can we apply Fourier transform for this? Yes, why not? It's all periodic. But resulting transform will assemble not a periodic signal, but the sequence. We need transform for one pulse. I have artificial created sequence of a periodic signal, but it's my work of my hands. It's crafted. Real should have only one. Problem. But we can do one trick. Take a look. Signal is periodic. What I'm doing? I'm shifting the time span. Periodic, oh. No period found. For my scope, at this moment, signal is no longer periodic. Why? Because next pulse occurs outside of the observation window. For my scope, time starts here and ends here. If the next one, now for scope it's periodic. It can calculate frequency, period, no problem. Non-periodic. Still periodic. When next pulse from the sequence, let's say shifts outside of the time margins, outside of observation window, for observer, for my scope, signal becomes non-periodic. So we had some non-periodic. It's one turn of the switch. Yeah. We can, let's say it was something like this. We can create a sequence. So let's say it comes from minus infinity to infinity of plus m period. We can create a sequence they have a t capital, seconds, milliseconds, or what between them. And now, for this sequence, Fourier transform is null, because the sequence can be treated as a periodic signal. Now, the trick. Shift period to infinity. We can do it on a table. Mass rules. See, here I shift next pulse outside of the scope, or let's say time window. For scope, here time ends. For us, everything outside infinity not existent. Apocalypse escape.
Doomsday is here. Who would bother about some pulse? So it's a play of mind, but we can assume sequence of pulses where repetition time is, let's say, shifted to infinity. We will see the same picture what my scope see now. For scope, signal has no period. While it is periodic, generator still produces pulses. Non-periodic, periodic. It's my blah blah blah. I'm always afraid of minus sign. So we have a signal sum m minus infinity to infinity t plus m t capital, and let's perform a Fourier transform. Let's define as omega k k t double p divided by period. It will allow us to calculate complex amplitudes. It's an amplitude of Fourier law at a particular frequency, and it will be 2 divided by period. We should integrate in t by half margins our signal a power j omega t. In fact, it's a classic form of Fourier transform. At this moment, nothing special happens. But let's do it. Let's shift period to infinity. How many pulses we will see? One. One original. The one what occurs at 0 time. Previous will happen before this world is created. What a pulse. God didn't save this world. And next one will occur after the doomsday. Who cares about it? We will see only one original. This means what observable signals in real is only one original. And we will see complex amplitude at the frequency being 2 divided by time a power j omega time. From minus infinity to infinity. Nice formula, isn't it? Only one problem. This one goes to 0, yeah? Divided by infinity. Looks stupid, no? I will get 0. For classic row, I will get 0. But this part is not 0. So theory of signals introduces a special function. It's called spectral function. It's an abstract. Such functions do not exist in our world. It's
classic Fourier law for periodic signals yields us, with the help of Fourier transform, we will get signal as a function of, yeah, or discrete frequency. This nice spectral diagram with a step 1 omega, 1 omega, 2 omegas, 3 omegas, and so on, represents, in fact, discrete frequency function, but this function is real, existing. This signal is existing in our world. Spectral function instead is pure abstract. It exists only here. So for our signal, for our spectral function of frequency will be infinity to infinity a power omega. Yeah. Spectral function. Some function of frequency, absolutely abstract, complex. Another strange mass object, isn't it? Strange mass object. What's the profit from it? Abstract function not existing in our space. What's good about it? Idea. Remember my idea with the transfer function. Let's say Ux, Uy. Uy was Ux multiplied by R divided R plus 1 against omega c. Familiar something? This part, transfer function of my network, it's a function of frequency, yes? Is it dependent from the input? No, it's dependent only on frequency. So, if we have some network which can be described as a transfer function, and at the input we have a spectral function of frequency, can function of frequency accept argument being function of frequency? Why not? Everything frequency. Result, output spectral function will be input spectral function multiplied by transfer function. Nice? Nice. Only one question. Where's the problem? Where the dog is digging? Do we need function of frequency? Sometimes yes, but mostly we will need function of time. I live in time. Our space is space of time. This function exists as some abstract object. It cannot be realized in our world. What do we need? We need inverse Fourier transform. We need a way to go back from spectral function to function of time. So we need Sy time will be a result of Fourier transform from output frequency function. We need this transform. This one gives us direct Fourier transform way
to, let's say, move from our world to some magic world of spectral functions, we need inverse transform. Without it, all this is useless. Nice idea, isn't it? Only one problem, how to get result. Result. First idea on our road to results. If it's okay for us, period smaller than infinity, classical Fourier law coefficients can be obtained values at discrete frequency as a values of spectral function at a particular frequencies. Classical Fourier law coefficients are values of spectral function taken at particular frequency. It's number one. Now, approach to inverse Fourier transform. Let's write our signal as a, what do we know about our signal? So we have signal as created as a sum of pulses. This can be represented as a Fourier law, infinity to infinity, a power, I didn't write, and time here, and it's equals to 1 divided by time sine minus infinity to infinity spectral function taken at particular frequencies a power yes, here it is. What we know. Signal was a sequence of pulses representable with Fourier law, and Fourier law factors or coefficients can be obtained as values of spectral function. Nice. Now question. What will be limit when period goes to infinity of S naught t? What we will get? Answer, original, that's nice. Now let's see what will be limit of this when period switch to infinity. What? Direct to infinity. One simple remark. We have a spectral diagram. 1 omega, 2 omegas, 3 omegas, and so on. What's the distance between spectral lines? One frequency. It's 1 omega or, yeah? So,
next frequency minus previous frequency equals. Yeah? Yeah. And what will happen when this nice period goes to infinity? This distance will become 0. And what is sum? When we have the spectral line closer, closer, and closer, at the end they will form one one solid figure. Yeah? And what the sum will become? Sum of infinite number of infinite close lines. What is? Yeah, integral. Or in geometric representation, area of figure. We will have determined. In reality, our task ends with area of figure. Funny. So, we will need to analyze of 1 double P. 1 second. I will infinity to infinity. F power 9 multiplied by difference. This will give us second. This will give us 1 divided by double B. We should integrate in infinity our spectral function from frequency F power frequency. Here it is. I can write it better like this way. Here it is. It is an inverse Fourier transform. Way out from frequency space to our time space. And what about him? He is an exponential pulse. Do I have time? I have a bit. Let's find a spectral function of this guy. It's easy. So we have pulse 0 when time is pre-0 and alpha time greater or equal to 0. Alpha here 1. See, but it's not important. What will be equation for spectral function? Infinity to infinity F power omega dt equals equals to from 0 to infinity m minus alpha m omega dt and equals to e divided alpha plus omega. Nice? Here it is. Image in a frequency space of this pulse. I cannot show it because it's a complex. But I can do one trick. First, to do something visible, I will represent it as a model and angle. It will be E divided by square root of alpha squared plus omega squared. I can draw this because it's a real function multiplied by e power arc tangents omega divided by alpha. More pulses for the god of pulses. Pulses. More pulses for the god of pulses. Let's assume some period in infinity. So, for complex harmonic, it will be 2 divided by period, a divided by square of alpha square plus k double p square multiplied by a power arc tangents divided by alpha. My scope is a bit smarter than it appears. Can you see the red line? I will switch. Do you see the red line? It's a result of Fourier transform. This red line, actual, this part, it's a magnitude of harmonics. That's how it looks. It's not ideal lines. I will explain why. When we will consider discrete time Fourier transform, I will explain why they are not ideal lines. But at this moment, this one is a time signal, and red line is an absolute values of Fourier coefficients. Now question. You see this equation. What will happen if I double the period? Watch. See? I'm making period double. And what will we see on the red line? They are close. Space between spectral line becomes twice smaller. I have quadrupole period, and we see just near of solid figure. See what happens? The bigger, let's say, or longer space between pulses, the closest are spectral lines. And that's not all.
The closer pulse, the larger or longer is the space between lines. Okay? It's a first idea. For such sequence, okay, I will compress it. Take a look. Look at the tail. See the bigger difference between line, figure became solid, and has a relatively longer tail. It's a moment number, let's say, number 1. Number 2, what will be reaction to rate of change? I'm changing the speed of the signal. I'm changing alpha. Maybe, wait 1 second. I will make it more visible. I will use additional 100,000 ohm resistance. Yeah. Now I have 2,000. I have 2,000 kilo ohms, and I will use the switch. And then connect it here. And where is the ground one? This one. When I push it, resistance changes from 200,000 to 50,000. Quadruple change. I change alpha 4 times. Look what happens with the spectrum. You see, lines are closer, and see the tails. See what happens with the signal tail. The faster change, the longer is observable, let's say, tail harmonics. Because we have case alpha. This means what? Faster rate of change, wider area of signal in frequent space. For your application, you have inverter, you have some power electronics. You just bit rise the frequency or took bit shortcut and used cheapest number. What's the result? Pulse became not shorter, but with faster rate of change. And you get wider area of disturbances. And what we get as a result? Electromagnetic compatibility failure. Somewhere here you have a signal, let's say data transfer. At a slow rate, it was outside of the influence tail. You have faster rate and everything fails.
disturbances from your inverter, from PWM, are in the range of your communication channel. Please. AMC failed. See how spectrum widens. The base is rate of change. But for example, you use smaller capacitor in a snubber network. This means what recovering voltage on the, for example, IGBT or MOSFET transistor grows faster. Frequency range of disturbance is broader, and you got disturbance in appear to be safe area where communication occurs. Or you disturb some public network and have problem with FCC. Change of alpha, change of period. Okay? But you see, it is possible to get frequency representation for non-periodic signal, but it will be not in the form of discrete frequency law, but in form of some mystical spectral function. But we have an inverse transform, so it's not so disastrous. Okay, I think it's enough for today. Maybe some questions? Yeah, it's just the beginning.